So question 25, we have Mars has an average orbital radius of approximately 1.5 times the average orbital radius of Earth. Calculate the time it takes Mars to orbit the Sun. So here is a good orbital motion question or an orbital time question, and this is where Kepler's law is very relevant, and it's relevant for motion around the Sun. And there are different forms that this formula can come in, but I guess the important one to recognize first is the form that you guys get in your formula book. So you guys get given the t squared over r cubed. So t is time, r cubed is the radius, is equal to 4 pi squared over g and capital M. So g in this case is the gravitational constant. M, on the other hand, I think I will note it here as well so you can see it, is a solar mass, or the mass of the object our planet is orbiting around. So what we can think of in terms of this is Kepler's law can also be written as t squared over r cubed is equal to k, and k can be Kepler's constant for, say, our sun in our solar system that we're orbiting around. And the reason for that is we know 4 isn't a changing variable, nor is pi squared, that stays constant. G is also a gravitational constant, and so is M for any object, be it Earth, Mercury. It doesn't matter because that's not the mass we use in our formula. It's the mass of our object we're orbiting, or otherwise our solar mass. So this whole right-hand side of our equation can be brought down as a constant. So we can think there is t squared for Earth, as well as r cubed for Earth. My bad. And that's equal to k. And then we also have a t for Mars with an r for Mars, and again following through, making sure that's cubed, both equal the same k. So we're at a really good starting point now for the rest of our question, because we can substitute both this formula one here and this formula one here because our k's are the same. Before we continue, we can add some variables to the rest of our question. So we can state what TE is equal to, as well as what RE is equal to. Before we go forward, I'm just going to quickly check what are we looking for. We want our answer in terms of days. So with that in mind, I'm going to set TE equal to 365. Now, we don't get the radius of orbit for Earth in our question, in our formula book, because it's an elliptical shaped orbit or an oval shaped orbit. So I'm going to leave that as RE, but I'm going to say that RM for Mars is equal to 1.5 times RE, because in our question above, we have it stated clearly, the orbital radius of our Mars is 1.5 times the average orbital radius of Earth. So that's that statement here that I'm making. So the other statement that I wanted to claim was TE is equal to 365. So let's go through and set up our formulas now. So we said these two, equation 1 and equation 2, can be equal to one another. So TE squared is equal to T Mars squared, radius of Earth cubed, multiplied by the radius of Mars cubed. Our next step would be substituting into it. So we have TE, which is our 365 squared, over RE cubed. Still, we don't have a value for it, and you're going to see why I'm not going to put a value for it. But then we have our TM cubed, which is an unknown, what we're trying to calculate. And we said Rm is all the way over here equal to 1.5 Re. So I need to think, okay, what's 1.5 Re cubed? I'm just going to simplify it in this step. And we can now move over to this step. So our next step would be moving this over to that side, our simple algebra. So we can get 365 squared. I'm not going to simplify because doing the square of 365 is going to get me quite a large number. We can get it to a point where all we need to do is just punch it into our calculator and we save on any rounding issues. So 1.5 Re cubed, and we can bring this out, put a multiply here. Say we've got 1.5 cubed and Re cubed all over, again, Re cubed. We see Re on the bottom and we've got Re there. We can cancel it out. Our next step over here would be now 365 squared. And sorry, I forgot to put the Tm, what we had left over, squared multiplied by 1.5 cubed. Should be a decimal there. And we can move our square over. We get the square root is equal to t. And then we've got something nice that we can just punch into our calculator. And when we put it into our calculator, we end up getting a Tm equal to 670.5. And we have a look what we're trying to the nearest whole number. And in terms of days, so to the nearest whole day, we end up getting 671 days. So this is a little bit of a longer explanation and a little bit of background to some of Kepler's formulas and how we make the conclusion here. I wouldn't expect you to take this long to get to a solution in the exam. But it's important to, when you've got the opportunity to take time and think about things, it creates a better understanding.